So, thank you. So, welcome. I hope everyone's having a good conference, good afternoon, so on. I appreciate I'm the last talk before the keynote and then the all-important beer, so I'll try not to go on for too long. But today I'm going to be talking a little bit about how you can simplify your backend development and infrastructure using my favorite programming language. So quickly about me, I'm CTO at a company called Rover, where we take code like this, turn it into graphs like this, and then we do all sorts of analysis to make sure you're not pushing your bugs into production. But I'm also a YouTuber, as mentioned. I make programming content when I can find the time. You can find me, it's just Isaac Harris-Holt. So, if I told you right now to go and build me a backend API for a new project idea, what technology would you choose? You've probably got one in mind. Great. But now I also need you to cache external API calls in multiple different caches and maintain some long-running background process that can read and write from those caches at regular intervals. So, from what I know of most developers, you've probably already added Redis to your stack and maybe a background processing library. And some of you out there have already started thinking about microservices. I can tell. But I have one last requirement. This API must never crash. Damn. Time to rewrite it in Rust, I guess. But no, there is, of course, a better way, a functional way. And that way is the type-safe, simplicity-first programming language that's expertly baked for massive concurrency and high availability with effortless scaling. I am, of course, as you can tell by my t-shirt, talking about Gleam. So, Gleam describes itself as a friendly language for building type-safe systems that scale. Let's break that down just a little bit. It's quite friendly, so it's got a simple, familiar C-like syntax. I appreciate it's not necessarily familiar to all the ML fans in the room, but for most of the population, there you go. It's also a very small language. There are only 22 reserved keywords in the compiler, and actually only 15 of them are currently in use. So there's not much for you or your colleagues to learn. And the whole thing is, of course, type-safe. The compiler will do what it can to make sure your programs are correct. And types can usually be inferred by the compiler. So type annotations, most of the time, are actually optional. Importantly, like I mentioned, Gleam is for systems that scale. Now, Gleam doesn't have its own runtime. Instead, Gleam can compile to JavaScript. But on the back end, it's most often compiled to Erlang to run on the Beam virtual machine. The Beam is this incredible piece of technology that's designed to power global systems like communications networks. And Gleam can actually take full advantage of that to take your programs planet scale. This talk is not going to be planet scale. It's going to be centered around a fictional little web server project. It's a simple API for getting data about Pokemon. Now, you don't need to know anything about Pokemon to understand this talk. We're just going to be building an API that has two endpoints. /Pokemon/name for getting information about a Pokemon, and /battle name1 name2 to get the results of a battle between two Pokemon. So, let's talk types. Modern languages often have a static type system that lies somewhere on the scale of it's kind of there, but it doesn't do anything, to Turing complete. And if any of you have seen this project, it's kind of crazy. If you haven't, just search Doom in TypeScript in the type system. But Gleam, thankfully, is not quite like that. For the academics in the room, Gleam uses a nominal type system based on Hindley-Milner. And for everyone else, we're using cutting-edge technology from about the 1970s. Now, Gleam has all your standard primitives for things like strings, ints, floats, booleans, and so on. And of course, it has lists and tuples. But if you want custom types, you'll be writing code like this. This is a record type. In this example, we have a type called Pokemon with a single constructor, which is also called Pokemon. And here's us constructing a value of the Pokemon type. But some types can have multiple constructors, like an interactable object that we might see in a Pokemon game. and it's possible for these constructors to take no arguments. So, generally, if you want to represent something akin to a struct, you'd use a record type with a single constructor. If you wanted something more like an enum, you'd have multiple constructors with no parameters. And of course, you can mix and match. But if you want to know which constructor something was created with, you'd use pattern matching, a bit like this. And what's really nice is that the compiler will scream at you if you miss any patterns. So don't worry, your programs will not be crashing because you've missed something. And you can also pattern match on lists, tuples, and you'll have exhaustiveness checking on all the values there too. Now, Gleam has a built-in record type called result, which is generic over two types, an OK and an error type. And this is used for error handling throughout Gleam code. A lot of you will be familiar with it. I won't say the word, but rather than throwing exceptions, we know potential error sites at a glance. Cool. So we can imagine we have a Pokemon type that might look something like this. And it might be represented like this in our JSON responses. So, moving on. We're building a web server, so of course, we need some concurrency. As I mentioned earlier, Gleam on the backend typically runs on the Beam virtual machine. Concurrency on the Beam works a little differently to what a lot of you are probably used to, except if you're an Elixir dev, in which case, please bear with me for like 2 slides. Instead of a JavaScript-style event loop, or managing communication between threads with a mutex and a prayer, the Beam runs on a number of processes. Processes don't have shared memory or a shared call stack. You interact with other processes by sending them messages. In Gleam, spawning a new process looks like this. It's quite simple. If you want to receive messages, you create what's called a subject. Other processes can then send messages to that subject for you to receive. That looks like this. Now, processes on the Beam are really cheap to create, and they're incredibly lightweight. You can have thousands of them running at any one time, and larger Erlang, Elixir, and Gleam applications often do. So, this fictional API that we're building is actually mostly a transformation layer over an existing API called the Pokey API, because I'm too lazy to store all the information myself. The Pokey API follows REST standards pretty strictly, so when you get a Pokemon, rather than getting all the details about things like its moves, you get links to them instead. Which is great if you're running in a browser. If you're building an API, But we need more details about the move, like its type and its base power. So we're going to be making an additional request per move returned. And of course, rather than waiting for these to complete in sequence, we're going to do that concurrently. This code uses a parallel map function to iterate over the list of moves in parallel, fetching them. It works by creating a number of processes, one for each move in fact, though the exact details not really that important right now. What's important is that Gleam can handle all of these and it won't break a sweat. We're talking 100 moves max, so it's not huge. But by the way, this let assert syntax, it will just crash if a variable doesn't match the pattern you're expecting. And in library code, that's a bit of a no-no, don't do that. But in application code, absolutely fine, and we'll get into why later. So, I promised you'd be able to replace some of your infrastructure as well as just improving your code. So let's take a look at caching. One of the awesome features of the Beam is called Erlang Term Storage, or ETS. It's an in-memory database that allows you to store any Erlang value, and therefore any Gleam value. Not just anything that's serializable to JSON. You can store functions and everything. It's great. So we're going to use the Carpenter package, which is a Gleam wrapper around ETS. And we're going to say that a Carpenter table with string keys represents our cache. Carpenter includes kind of all the functions you'd expect to be able to use, like creating new sets, inserting and removing items, and so on. And on top of all of that, I want to add a read-through function. And this will try to first get a value from the cache. When it's not present, it will run a function to get that value, caching it if successful. And this code works really well, but it's really ugly. I mean, just look at how many levels of indentation. Talk about Pyramid of Doom. It's time to make use of another fun Gleam trick.
Yeah.
Remember those 22 keywords I mentioned earlier? My favorite one is the use keyword. It's just a bit of syntactic sugar, but what it allows us to do is flatten out our code when we have a higher order function whose last argument is the callback. And that looks like this. I'll replay that again because the animation is not amazing. There you go, flattens it out. So, if we take this function, combine use with some of the functions from the Gleam/result module in the standard library, we can turn this nightmare into this. The try and try recover functions that you see here just update the OK or error value in a result by passing it into another result returning function. Combined with use, we're immediately back to one level of nesting, and it's much easier to grok the happy path of the code and what's actually going on. And now we can write a fetch Pokemon and fetch move function using read-through. And of course, we can apply use here too. Cool. So we've pretty much got the logic for one of our endpoints now. But what about the other one? Pokemon battles are pretty complicated and can be quite compute intensive to simulate. Caching the results of a battle is great, but what about the first time a particular pairing is requested? Is that request not going to be a lot slower? Well, yes, obviously, and there's no way to get around that without computing every single possible combination, which is a lot. But we can try to mitigate some of that by pre-computing battle results in the background. In Gleam, we can create long-running background processes called actors. These maintain their own internal state and can process incoming messages to update that state. And we'll use this to create a battler that then runs those battles in the background, storing the results in a cache. We'll start by defining a type for the different messages we might want to send to our background process. The process battle message is pretty self-explanatory, and we also have a shutdown message so we can safely stop the actor at any point. Although the Beam is pretty good at handling shutting down processes when your application stops or allowing you to just kill them outright, it's nice to have a proper shutdown so we can scale down safely if our service is under high load. This type represents our internal state, which holds the actor's own subject so that it can send messages to itself. It also has the handles for our Pokemon cache and a new battle cache that stores the name of the winning Pokemon for a battle. Now we get to the meat of things. We need a function to tell our actor how to handle incoming messages. This is effectively our loop. So, when our actor receives a process battle message, it'll battle the two Pokemon, storing the winner in the cache. And then finally, it'll schedule a new battle between two random Pokemon that already exist in the cache. And this is done with a 3-second delay, because we don't need the battlers to be busy all the time. But even if they were, and they were using a lot of CPU, the Beam can make sure a single process won't completely pin it, even if other processes are executing. And finally, we can use the actor module from Gleam OTP to start the actor. And we can start pretty much as many of these as we like, depending on how many battles we want to have going on at once. Now, independent processes receiving and responding to messages sounds a lot like microservices, but inside your application and spinning up and down pretty much instantly. Makes you think, huh? Perhaps you don't need 300 lines of Terraform to deploy your CRUD app? But what if one of our battlers dies? It's time to talk faults. Now, as I mentioned earlier, Gleam is a language where you mostly program defensively. Results tell us in the type signature where an error could happen, and we can make a best effort to recover from it. But sometimes something goes so horribly wrong, there's no way to fail gracefully. And in that case, we want to crash. In Gleam, one of the ways we can do that is this panic keyword. And I also mentioned the let assert syntax earlier. Again, the Beam, pretty special here. I said that processes can't share memory, but in fact, unless you specify otherwise, they are completely isolated. So, if one process crashes, we can just kind of let it die, and it's not going to take the rest of the system with it. The framework that most Gleam backend APIs use is called Wisp, and it creates a new process to handle every single incoming request. And if something blows up unexpectedly, we just drop the one request. The rest of them go through fine. But actually, that was a lie, because we're not even going to drop that request. In Gleam, and on the Beam in general, you can choose to monitor a process and get a message when it dies, or if it dies. Wisp does this, and if it notices that one of its requests processes has died, it'll just respond with a 500, so you don't need to worry about that. And the Beam itself actually internally can use this monitoring concept to create something that's called a supervisor. A supervisor is a process that, well, supervises other processes, and it'll restart them if they fail.
Good.
Most Beam applications are one big supervision tree. You've got layers and layers of supervisors all looking after child processes, which can be worker children, or more supervisors. And if something crashes and you can't recover from it, okay, it's supervisor will crash. And if that can't be recovered, its supervisor will crash. All the way up until part of your program is completely gone and then can be restarted safely. This is what we mean when we talk about fault tolerance on the Beam. Practically, we can accomplish this in Gleam really easily using the Lifeguard package. It allows us to create a worker pool and broadcast messages to all our workers or send messages to one at a time. And if any of our workers crash, Lifeguard will take care of restarting them and tracking the subjects for all the active processes internally. Once again, this is a declarative way of specifying a number of processes that need to be running, restarting them if they fail. But I'm not going to go quite there yet. Thank you. Obviously, this was a small example, but hopefully you can see that as your project requirements explode, running Gleam on the Beam means that your code doesn't have to do the same, because we like our backends nice and simple. Thanks.
Thank you. Thank you. We do have a couple of minutes for questions, if there are any.
Hi. I'd like to ask about parallelism in the sense of, like, I work with TypeScript, and my way of building things is, yes, there'll be 300 lines of Terraform code, there'll be, like, numerous Lambdas, and a lot of time I assume there's, like, sometimes could be, like, 1,000 invocations of these Lambdas, and they may mean that there are multiple physical machines running maybe multiple processes, multiple node instances. So how does this scale for Gleam? Like, what if you're like a single server or like virtual machine is not enough? How does the this whole thing OTP like handles this, and how does Gleam? And the second bit was this recent thing about colored functions and how Java received the virtual threads and everyone else uses the async, and Gleam uses the use sugar for that. Yep, thanks.
Cool. So I'll tackle that sort of bit by bit. This is roughly the Beam architecture, very, very simplified. But essentially, each of your CPU cores on any node will get a scheduler, and a scheduler will be responsible for running multiple processes. What happens is each process will run for a set amount of what are called executions. What that is will vary depending on the program running. But you can think of it as just it will complete a set number of instructions before moving on to the next process and so on. Now, I've got this big OS in what I think is blue. You'll have to excuse me on that one. But the thing is, the Beam doesn't really care about that. So your one node not being enough question, well, if it doesn't care about that, then all it cares about is the number of CPUs. And the Beam actually distributes really well. So you can connect a number of nodes together, and as long as you have a process ID, or in Gleam's case, a subject to send a message to, the Beam does not care if it's on another computer. Nothing is shared anyway, So the problem of, I've got some shared memory pool on this node that isn't available on this one, it's not there. It just doesn't exist. The Beam was built for this kind of global scalability from the beginning. And function coloring, there is no function coloring. Anything can be run on another process.
Great, thank you. The keynote starts in 5 minutes, so I think I'll give people time to go. But if you have questions, yeah.
Is it?